our first two lectures, we discussed some of the defining characteristics of the study of matter and its properties. We defined a few of those properties and how we communicate them. We saw how chemists basically study everything, but that we do so on a scale unique to our science, the scale of atoms and molecules. We saw some of the ways in which chemists deal with the minute scale of chemistry, using scientific notation to express huge or minuscule numbers. And we also saw how sometimes we even create our own units to make measuring critical values like distance, masses, and amounts easier. So, what should we measure and characterize first? Where do we begin our journey together? Well, as strange as it may sound, after all the lip service that I just paid to matter in the preceding lectures, I'm going to spend this lecture focused on something which has practically no mass at all. Today, we're going to talk about light. So, why am I bending my own definition of chemistry in Lecture 3 of the course? Well, the answer is quite simple. Because it's light that we often rely upon to probe the properties of matter at the atomic and molecular level. The word light to chemists is really better defined as electromagnetic radiation. In common discussion, we tend to use the term light to mean that portion of the electromagnetic spectrum which we can see. But in truth, there's much more to light than what we can see with our eyes. And we'll broach that topic very soon. But for now, let's think about visible light, because it's what most of us are used to thinking about. In general, light interacts with matter in several ways. It can undergo absorption, emission, reflection, refraction, and diffraction. Now, you probably observe most, if not all, of these kinds of interactions within your own eyes on a daily basis. You put on sunglasses whose lenses absorb light to protect your eyes. You flip a light switch to induce matter inside of a bulb to emit light. You use reflected light in the mirror in the morning as you get ready for the day. If you walk by a fish tank or look through a glass of water, you've probably observed the effects of refraction, as objects seem to be in one location when observed through the container, but are actually in another position behind it. Diffraction is another phenomenon that leads to the appearance of rainbows in the Earth's atmosphere. It happens when waves of light interfere with one another as they interact with particles in our atmosphere. All of us use the interaction of light and matter to learn about our surroundings on a daily basis. What chemists do is often no different, though sometimes a little bit more complex. So why should a chemist be so concerned with light? Well, think about this. When you step outside on a sunny day, you can feel the warmth of the sun's rays on your face, right? So why does your face feel warm? It feels warm because the light is acting as a vehicle for energy. Light interacts with atoms and molecules in very specific ways, delivering and transporting energy that we can measure using devices as simple and familiar as the human eye, or as complex and technical as million-dollar electronic devices. Many techniques employed by the modern chemist to characterize matter use electromagnetic radiation, light, to do so. No matter how you look at it, when studying the properties of atoms and molecules, light is almost always part of the equation. Anytime you look at an object, you're collecting information about how light interacts with that object. The absorption, emission, reflection, refraction, or dispersion that you'd observe depends on the atomic and molecular properties of the material involved. So one could say that in order to metaphorically shine a light on atomic and molecular structures of matter, we have to literally shine a light on that matter. Exactly how chemists use light to study matter is a topic that we'll investigate in future lectures. But before we can begin characterizing how light interacts with matter, we first need to understand light itself. So during this lecture and the next, we're going to spend a bit of time getting familiar with light from the perspective of a chemist. Light is something so familiar to us that we often take it for granted. But have you ever stopped and contemplated what exactly is light? Well, what is light made of? How does it move through space? And how does it carry energy? Is light simply a disturbance in matter, like sound or seismic waves? Or is light actually matter itself, a stream of particles moving in a beam? These questions perplexed great thinkers as early as the time of ancient Greece, when Aristotle espoused one of the first theories on the nature of light, describing it as a disturbance in one of his proposed elements, air. This description makes a little bit of sense because it's consistent with light being a wave, which we know from experience can move and carry energy. Around the same time, though, Democritus, another Greek philosopher, posited that light might instead consist of very small indivisible particles, something akin to atoms, but with an identity and makeup all their own. This idea also makes some sense. A stream of particles would move and carry energy with it as well. Although both of these theories about the nature of light would seem to explain its ability to carry energy, they also appear to be diametrically opposed to one another. It would seem that light has to be one or the other, a wave or a stream of particles. Neither Aristotle nor Democritus had the necessary technology to test their theories scientifically, of course, and this left the true nature of light up to debate in their time. Now, little did either of these great thinkers know that their debate over the composition of light would have to wait more than 2,000 years to finally be resolved. Fast forward those 2,000 years. Even as Europe was exiting the Dark Ages, Isaac Newton and his contemporaries were carrying on the struggle of defining what makes up light. Newton's famous corpuscular theory sided with Democritus, arguing that only particles could be refracted by a prism, as he so famously had done to observe the visible spectrum. But another famous scientist of the time, Christian Huygens, countered Newton's theory by suggesting that the same phenomenon could be explained as waves of light propagating at slightly different speeds through two different media, in this case, air and quartz. So, in the 1600s, 2,000 years after Aristotle and Democritus touched off the discussion, the debate over the particle or wave composition of light seemed no closer to a conclusion. In this lecture and the next, we're going to consider this age-old debate using some of the first scientific observations brought to bear on the question. And today, we're going to hear the case for the wave nature of light. When I say the word wave, what comes to your mind first? Maybe you thought of waves of water lapping against your favorite beach spot. Perhaps it conjured thoughts of sound as it travels through the atmosphere, or shock waves from an earthquake moving through the Earth's subsurface. These are all fine examples of waves. But there is an even more common but slightly less obvious type of wave that we encounter on a daily basis. Waves of electromagnetic radiation, light. They're almost constantly passing by us and even through us. Now, we can look at water waves as they move across the ocean, or shock waves from an explosion as they radiate outward through the air. But the wave nature of light itself isn't as easy to see. It eluded some of the greatest thinkers of the human race. So, how do we know that light is a wave? To answer that question, we have to pay a visit to an English physicist by the name of Thomas Young. Born in 1773, Young grew up studying the work of Isaac Newton. And I'm sure that Young had a great deal of respect for Newton's work, but he wasn't buying Newton's corpuscular theory. And as a young researcher, he set out to disprove it. Young made many contributions to the science of physics, but arguably, his greatest is an experiment that seemed to prove indisputably that light consisted of waves. Not only that, but it was such a simple and elegant proof that it could be verified by anyone using items that you might have right in your own home. Don't believe me? Watch this. Salt, sugar, vinegar, water. All common everyday ingredients that you'll find in your kitchen at home. And we tend to think of these materials primarily as things that we bake with. But those are also chemicals. And that gives us a unique opportunity in our kitchens occasionally to learn a little bit about chemistry without having to go into the laboratory. So from time to time, we'll come here to the kitchen, and I'll try to show you some things that you can do, and maybe a few things you've already done, that illustrate the chemical principles that we're discussing. And today's discussion of light is our first opportunity. But before we get to that, let me talk a little bit about how to safely do some of these experiments in your kitchen. Although it's a relatively safe place to be, we still want to protect ourselves as though we were in a laboratory, and so I'll be doing that as well. So I brought along a few pieces of personal protective equipment to be absolutely sure that I leave this demonstration in the same condition that I came in. Now, the first of those are chemical safety glasses. These are impact-resistant lenses with a curved brow and side splash guards, so that if any liquid gets splashed into the air during my demonstration or any solid material comes towards my eyes will be protected properly. Since today we'll be working with laser light, I've also brought some special protective laser glasses. Now these are very inexpensive and easy to find online, and it's important that you get the right color. And I'll show you this one more time, but let's take a look at it right now as well. I've chosen red. And I haven't chosen red because that's my favorite color. I've chosen red because the laser I'll be working with is a green laser. So that might seem a little strange, right? Why did I choose red glasses to protect my eyes from green light? Well, the reason is that the glasses appear red to us because if I turn on my red laser, you see that red laser light goes straight through the glasses. These glasses don't absorb red light. On the other hand, when I shine green light on these glasses, which hopefully I won't do at all, but just in case I do, they will absorb it because green is the complementary color of red. So be absolutely sure you understand which color glasses you need if you want to try this experiment at home. Occasionally, I'll also use some nitrile protective gloves. And these can be purchased at your local grocery or hardware stores relatively inexpensively. And they'll protect your hands from some of the deleterious effects of some of the chemicals that we're going to work with, like strong salt solutions and vinegar. So, without any further delay, let's think a little bit about Thomas Young's experiment and how he finally settled the 2,000-year-old debate over whether light is a wave or a particle. To begin this experiment, I'm going to use a green laser. And I've already attached this green laser to a little holding mechanism here on a ring stand. You won't have to necessarily do this. You can hold these in your hands, but to make it a little bit easier for the purposes of our demonstration, I'll be doing that. And just to demonstrate to you really quickly that I've chosen the right safety glasses here, you recall how it looked when I shined my red light through the glasses. This is the green laser, and this is the green laser through the glasses. You should be able to see very clearly there. They're absorbing the light. So these glasses will protect me just in case a little bit of this laser light bounces back. And I'll put that right back where it came from. All right, and we're ready to go. So I have my laser ready to go. I have my eye protection ready to go as well. Now, the next thing I need to do is create the famous double slit. And to do that, I'm going to use a pocket comb. So a pocket comb that has very fine teeth, the finer the better, is going to provide what we need to create a double slit. And all I need to do is cover up this comb so that only one of the teeth is exposed, creating a small gap on either side for light to pass through. So I'm going to do that now. Using my black electrical tape. I like to place the comb on a nice, bright, white piece of paper. That way I can see the teeth as best as possible. So that only one tooth and the gap between it and its neighboring tooth is exposed. And then I'll place that piece of tape down nice and tight. Right. I'll do the same thing on the adjacent tooth to create my second slit. So I'll take another piece of tape. Very, very carefully place that. Over the comb there, and if I hold it over the paper, hopefully this will show well. You can see that there is a slit right there, actually two slits, one right next to the other. So that gives two potential pathways for my light beam to pass through. So now it's time to finally recreate Young's experiment. So to do this, all I have to do is point my green laser beam at the slit that I have created, the double slit that I've created, in the comb. So I have one prepared here, and I'm just going to set that up so that it projects onto a wall. I'll put my laser in place. And because I have to sight this laser very specifically so that it hits that beam, that means I have to look at it very closely, and it's going to be very close to this reflective tape. So I'm going to put my eye protection on now, and I'll turn on my laser. So now we can see what's going on here. A single beam passes through two slits. We would expect, if they're particles, to see two dots on the wall. But instead, I see a linear array of dots, many, many, many small dots of green light. And an effect like that, in a system like this, can only be produced by a wave. Young, of course, didn't have lasers, but he did have sunlight. And what Young observed was the same phenomenon that we just did. White light focused on a double slit created a similar interference pattern. So what do those lines of dots in our laser projection really mean? How do they prove that light's a wave? Well, it's true that a beam of particles should have produced just 2 dots in that system. And that's easily understood and very clearly disproven by what we saw. But we haven't yet answered the question, how does the pattern confirm wave theory? Well, remember, we saw multiple evenly spaced bands of light. These bands form because as light waves pass through the slits, they radiate outward from them. And this creates a pattern of interference in which waves generated at the different slits occasionally interfere. This creates the fanned-out pattern of light bands that we saw in our experiment. So at last, we have proof that light must be a wave. And because it's a wave, light has all the same characteristics as any other wave. The most important of these characteristics for our discussions will be wavelength, velocity, and frequency. Here's an example of the kind of wave that we can think about when describing light. A regular repeating wave. Now, this wave has repeating troughs and peaks, and they're always occurring the same distance from one another. Now, we call that distance between neighboring peaks or troughs a wave's wavelength. The wavelength is often represented using a lowercase Greek letter lambda, and that's the convention that we're going to use in this course. Now, set the wave in motion at a constant speed. Now, the speed of a light wave would be about 3 × 10⁸ meters per second, fast enough to circle the Earth in about 1/10 of a second, or reach the sun in just 8 minutes. So for our demonstration, we're going to have to go a little bit slower. But let's get this wave moving anyway. Now, I'd like you to notice that when we do this, equivalent points on neighboring waves will pass a position at regular intervals. Now, this is known as a frequency, which is commonly shown using a lowercase Greek letter nu. We report this in units of cycles per second, also known as hertz. You're probably most familiar with this unit from its application in FM radio, where the station's frequency refers to the frequency of radiation used as a carrier signal to broadcast that radio station's transmission. For example, 103.5 megahertz means that the carrier signal has 103,500,000 cycles per second as it passes by. Now consider this. If I double the wavelength, look at what happens. Fewer peaks pass by per unit time. So wavelength and frequency are inversely related to one another through a constant equal to a wave's speed. This could get a bit complicated, except for the fact that the speed of light is constant. So when we limit our discussion to waves of light, wavelength and frequency can be easily interconverted using this relationship. Lambda equals c over nu, where c is the constant speed of light, 3.0 times 10⁸ meters per second. So, light has wave-like properties, which means that we can measure these characteristics and classify light based on those properties. Isaac Newton himself handily proved that light could be separated by passing it through a prism at the appropriate angle. And when he did this, he demonstrated what we commonly call white light is actually a collection of many different colors of light. Newton coined the term spectrum to describe this collection of different colored lights. Scientists today know that these different colored lights are the result of slight variations in their wavelengths. In this case, with visible light, we're talking about wavelengths that range from about 400 to about 800 nanometers. To put that into perspective, some of the smallest cells in your body are about 10 micrometers wide, or 100 times larger than the wavelength of light that we can see. Now remember that light is a term that most of us use to describe electromagnetic radiation your eyes can detect. But in truth, we would be talking about visible light in a situation like this. Our eyes are a remarkable product of our evolution, but they have their limitations. And in this case, it turns out to be a pretty severe limitation. You see, in 1800, an English researcher named Sir William Herschel discovered that prisms separate not only visible light, but an invisible form of light that falls beyond the red end of the spectrum. He named this infrared light because of its location beyond the red. Just a year later, in 1801, Johann Wilhelm Ritter discovered another invisible form of light, capable of darkening silver salts. And this type of light fell outside of the blue or violet end of the visible spectrum. So Ritter called this ultraviolet light. So light comes in far more forms than that which we can see with the unaided human eye. Even Herschel and Ritter couldn't possibly have guessed just how far outside of the visible spectrum light really goes. It's actually quite staggering. Scientists characterize each region of the electromagnetic spectrum based on the wavelength of light that produces it. And these wavelengths can span a remarkable range of distances, varying from lengths greater than a mile to smaller than the diameter of a single atom. When we line all of these possible wavelengths up from shortest to longest, we can see what a truly small slice of the spectrum human beings can see with the unaided eye. So, let's take a short tour of the electromagnetic spectrum as we understand it today. Here it is. At the extremely short wavelength end of the spectrum are gamma rays. These extremely high-energy rays have wavelengths so small that they're even smaller than atoms. Next in line are X-rays, light with a wavelength just about equal to the size of an atom. And X-rays have the ability to expose photographic film, just the way visible light does. But they carry so much energy that they can penetrate flesh, but not bone. And this has led to their use in medical imaging, as we'll soon see. Now, the former property allowed many researchers to use them as scientific tools in this way. Our next stop is ultraviolet radiation. Wavelengths of ultraviolet light tend to be near the size of many molecules. They're just about 100 nanometers across. And finally, we reach the visible light, that small slice of the electromagnetic spectrum that we use every day to observe the world through our eyes. But a slight increase in the wavelength, again, takes us into the infrared region of the spectrum. Infrared radiation is emitted by matter naturally around the temperatures that we experience here on the surface of the Earth. Now, this makes them very interesting from a number of potential applications, not the least of which is being able to detect the presence of warm objects in what we perceive to be complete darkness. Next comes microwave radiation, which has wavelengths around 1 meter. Microwaves have always been fascinating to scientists, but in recent decades they've become best known for their use in exciting water molecules to generate heat in the form of microwave ovens. And our final stop on our short tour of the electromagnetic spectrum takes us to radio waves. Waves so long that their wavelengths can easily span distances of miles. Of course, the most familiar technology associated with radio waves is the transmission of audio information. But just as with all other forms of radiation, we'll learn in this course that radio waves have other properties and applications exploited by chemists to help us understand the world around us. From highly toxic gamma rays emitted by pulsars at the edge of the universe, all the way down to radio waves which can pass through humans and buildings without causing any apparent harm. Light has a remarkable capacity to carry varying amounts of energy through space. Maybe even more remarkable than that is that chemists have devised ways to use all forms of light as probes for the structures and functions of molecules. So let's summarize what we've discussed so far in this lecture. We focused our attention on light, which can interact with matter in a number of ways that can help us to understand our universe. We discussed the millennia-long debate over the true nature of light. And in this lecture, we considered the wave nature of light, which describes light waves in terms of wavelength, frequency, and velocity. We saw how the wave nature of light is easily verified using a very simple experiment conceived by Thomas Young in 1803. Then we learned about the discovery of infrared light and ultraviolet light by Herschel and Ritter. Discoveries that brought to our attention that there is a tremendous continuum of electromagnetic radiation, most of which we can't see with our own eyes. We also saw how the wave properties of light, like wavelength and frequency, help us to organize electromagnetic radiation into a continuum known as the electromagnetic spectrum. So it would seem that the debate has been settled, but appearances can be deceiving. Not long after Young's discovery, yet another great scientist made a discovery that would once again ignite the debate over the true nature of light. We're going to hear his case for the particle nature of light in our next lecture. Occasionally, as time allows in the course, we're going to take some of the knowledge that we gain in a lecture or two and apply them to a problem that I like to call challenge problems. And this lecture gives us our first opportunity to do that. So let's ask a question about electromagnetic radiation and see if we can answer it using what we've learned. We're all pretty familiar with FM radio. Now, my particular favorite station here in the DC area broadcasts at a frequency of 103.5 megahertz. That's the frequency of the electromagnetic carrier signal that's bringing that radio station to my stereo in my car or my home. But the question here is, if that's the frequency of that carrier signal, then what is the wavelength of that radiation? They should be related to one another using an equation that we've already learned. Lambda equals c over nu. Remember, the proportionality between wavelength and frequency is described by this calculation. So let's answer this question now. We're going to start with a wavelength, and of course our target is to know how many meters that wavelength is. So let's use the information from our problem, 103.5 megahertz, right, which is actually 103.5 million hertz. So I have to be sure that I include that in my calculation. Doing my unit analysis here, I have megahertz cancel, reciprocal seconds cancel, and my answer will be in units of meters. This is what I want. So now I can run the math. The speed of light divided by 103.5 megahertz with a correction factor for the fact that megahertz is a million hertz, I get about 3 meters. So the wavelength of that radiation carrying the radio signal to me is about 3 meters long. It's taller than I am. Now let's try a different problem with a type of radiation with which you might be less familiar. X-rays. Now, X-ray crystallography is a technique used by scientists to divine the structures of many molecules. X-rays are useful for this purpose because they have extremely short wavelengths. As a general rule, you need a wavelength that's at least as small as whatever you're trying to observe. So, when it comes to observing atoms, we obviously can't use visible light. The wavelengths are just too long. But one of the more popular X-rays for this technique is one that is 0.71 nanometers. This is generated by electrically exciting molybdenum atoms. So our question for the day is, what's the frequency of that radiation if its wavelength is 0.71 nanometers? We have to use a slightly different version of our equation, right? Notice that I've isolated frequency now. So my calculation now reads frequency equals the speed of light divided by the wavelength, which is just a mathematical rearrangement of what we used previously. So I'm after units of frequency, meaning I'm going to put in my c divided by lambda. And of course, I'm going to have to remember that in this case, I'm dealing with a wavelength that was given to me in nanometers, but the speed of light that we used was in meters per second. So to correct for that, I'm going to put in a factor of 10 to the 9th nanometers equal to 1 meter. Unit analysis tells me that nanometers will cancel, as will meters, leaving me with reciprocal seconds. And the answer that I get is 4.2 times 10 to the 17th hertz. That's 420 petahertz. Not megahertz, not gigahertz, not even terahertz, but 420 petahertz. Nearly a billion cycles per second pass by when one of these X-rays is moving.